for 1 year, then another 1 year in Grenoble, and a year later went to University of Washington. He was at Welsh for a while, and then he was a visiting professor in Strasbourg, Harvard, and Freie University of Berlin. And he was scientific director of the synchrotron lab in Campinas, and the nowadays called CNPEN. And as I said, since 2015, he's at UFI, but he's moving to UFRJ once the pandemic is over. So, and today he's going to talk to us about his recent research. The title is Structural and Electronic Properties of Realistic Two-Dimensional Amorphous Topological Insulators. And as he already described it, he's gonna start with a general introduction and then present his results at the end. So I guess we can start. Let me see here. We have 29 people already, so and it's 2:05, so he can start. Thank you very much for accepting our invitation, and please go ahead. Thank you.
Okay, George, thank you for the invitation. It's a pleasure to talk to you about my research, and I hope I get you interested in the subject. I think it's very interesting, actually. And well, so I'm going to report about 2 papers. The first one is appeared 2 years ago, and then this one is quite recent. And I'll tell you why we split in 2, because we learned a lot of stuff in the meantime. And we are trying to make sense of realistic modeling of amorphous topological insulators. So the title has many words here, so I'll try to basically define what the meaning of these words while we move along. And also I'll situate what are kind of the challenges in the field, and then see how we go. Okay, so the plan is this. I'll talk some of you guys probably know, I mean, some of the backgrounds of topological insulator, the main elements. I think, well, at least Tobias has worked on that. And I guess many other people in the audience. And then I'll give a brief review of what is called non-crystalline topological insulators, and then I go to amorphous materials. This is old stuff. And then I'll try to say some words about can we have actual realization of amorphous topological insulators? Can we realize this in actual materials? And this is basically the effort we have been spending about 2 years now, and with good results. So we learned a lot, and I'm going to share with you this. So let's start with some provocative slide, right? So I'm going to show you the challenge of being a theorist trying to understand electronic transport. And the problem is scales. So you want to have a theory, a unified theory, that describes the resistance of materials that go from insulators, say 10 to the 24 in these units here, up to metals which have very little resistance. And if I can actually even put superconductors here, and then I'll blow up the scale. So if you look at the span here, it's more than the challenge of these guys in field theory, the great unified theories. And the thing is that as a theorist, you want to have a single tool, or a well-defined tool, to approach all these materials, and not to patch here, do a model here, a theory there, etc., etc. And this is rather difficult, right? I mean, this is obviously an exaggeration because we actually know why some materials are such a poor conductors and others work pretty better. But, okay, so this is just to catch your attention. The most, I mean, if you think about bulk materials, the most established theory is the Kubo one, right? And I mean, there are different ways of approaching the Kubo conductivity, and you can do it in different levels of sophistication. But in linear response, actually, it's perturbation theory, and you can actually derive these formulas, the Kubo conductivity, in a few slides. I mean, in few hours, you get the formula right, starting from scratch. The idea is that you put an external field. Let's make it time-dependent. Then you define the electric field. Perturbation theory, you know how to work up to first and second order. This is first order. And then if you want to know the contribution of the kth state to the current, you just take the sandwich and just equating out the energy, the electric field, you get the conductivity tensor written in these terms. And this is a way that people actually love to evaluate the Kubo formula, because if you know the band structure right, and you know how to write these operators, you know the dispersion, you know the, let's say, the energy of the bands, then this is a very easy task to do. Even if you have some interesting mechanisms that, for instance, electron-phonon, electron-electron interactions, then you start dressing this propagator and you have a fair assessment of the transport properties. Obviously, George, who is an expert in strongly correlated systems, will object, and Louise is also there, and Ed, so well, the whole crowd is working on different subjects, and they'll say, oh, it doesn't work, because actually you have to do much better theory than that to explain the transport properties of a whole class of materials. And indeed it's true, but it boils up to, I mean, you can always think that if you write propagators, Green's functions, you have a pretty decent theory, okay? Now, there is a very different approach to understand transport properties, which is a more like a geometric one. And it actually got very popular in the last 20 years or so, because people understood that bulk properties are nice, but once you deal with nanostructures, then you have to account for confinement effects. And basically the champion of this was Landauer and also Büttiker, and they came up with the idea that actually you have to understand the electronic properties of a confined system, and then confinement actually plays a big role. For instance, if you have a wire with different transversal channels, and then you have this band dispersion across this in the transversal direction. So this is Kz. Sorry, this is the longitudinal momentum, and this is the transverse, and this is the band structure of this guy. So this state here, oh, it's the other way around. The blue should be down, and the green should be the upper. Sorry. So the lowest energy has 0 nodes, right? And if you have a Fermi energy crossing here, then you have only 2 states, right, that are allowed, that move forward. Because if you take the derivative of the energy with respect to k, the velocity associated to that is that you have 2 more forward-moving states and 2, let's say, backward-moving states. And these are the two channels that you have for the conductance, the transmission across this sample. And this has been observed, actually, if you put some, let's say, some experiments and you confine the electrons to a channel like a narrow constriction like that, and you start moving, I mean, if you start playing a game of making the constriction wider or narrower, you see these nice steps forming. And this is the situation illustrated here with two channels. And then you have this unit conductance. Okay, so this is actually the view of having let's say a nanostructure, a system where geometry plays a role, right? But coming back to Kubo, right, or the common wisdom, is that you actually explain this difference that I showed before between the conductance of metal, the conductivity of a metal, semiconductor, and insulator by looking at the, let's say, at the band structure and at the gap. So if you have an insulator, the gap is sizable, and then obviously there are no states to transport the electrons. And things are different when you have a semiconductor and a metal. And here you have different mechanisms of having mid-gap states or stuff like that. So you have conductance, and here conductivity is high. So, and then the cousin or the precursor of the modern topological insulators was actually discovered in the mid-80s and put this whole nice scenario into question, right? So, and this was the integer quantum Hall effect. And this standard picture that I just showed you, it doesn't work because, well, we'll see how. They got this Nobel Prize, Klaus von Kritzen got this Nobel Prize in '85, and the original paper is this. So what happens there, right? There, basically, the quantum Hall effect, you have a classical limit, and this you can compute with standard Drude formula. This is one of the first classes in standard condensed matter course. And basically, the longitudinal resistance is given by that. Doesn't depend on the magnetic field. Depends on scattering mechanism, effective mass, concentration, etc. And the transversal one depends essentially linearly on the magnetic field. And what people have observed late in the 80s, right, is that if the magnetic field is small, then okay, you find this nice linear behavior. And well, it's not really parallel here. But as you increase the magnetic field, the conductance, the transversal conductivity, resistivity has these steps, and the longitudinal has these peaks. Okay, nice and interesting. So how do you explain that with the standard picture? Actually, you don't. And so this is another view graph of what happens. So you basically have this interesting levels here, the Landau levels that explain more or less the position of these peaks, and well, it's the same transparency as before. Okay. The idea there is that you have to mix this Landauer picture with the Kubo, and then you get the whole thing. So this was an important paper by Halperin, where he said, well, basically you have these levels which are quantized, and then between levels you shouldn't have the naive expectation is that you have a gap, and you shouldn't have any kind of signal. But actually, he understood that these levels, they don't disappear, and once you approach the edges of the circle of the sample, you have these curves, and basically the levels curve, so due to confinement, and then you repeat this very same design or very same picture I described before for the narrow channels when you consider nanostructures. These structures are by no means small, but interesting enough, they exhibit integer quantization of the steps due to these channels, individual channels. And this you can explain nicely in this picture. But then at that point, people were very happy that they had a nice theory to explain the steps of the quantum Hall effect and all that. But for some people, this is never enough. You want to unify. You want to have a unified picture. And there were some physicists which were very unhappy that the Kubo formula wouldn't give the correct result, at least without further analysis. And the hero is this guy. So he insisted in having a different kind of explanation, and he wrote with Komoto, Nightingale, Denise, this important paper where they explored the Kubo formula, and they wrote the whole conductivity using the Kubo formula, and they simplified everything they could. They considered also a periodic potential, which people criticized at the time because it wasn't realistic. Things in the whole system is very disordered, etc. So they had to use very many simplifications to show actually that under some strict circumstances, the conductance would be quantized, right? The conductivity would be an integer number of E squared over H. And this is the correct result, right, for a model which was at that time criticized. Right, and that story I got from. I was a postdoc in Seattle, University of Washington, and that was much before David Thales got the Nobel Prize. And he told me this story. He was already very famous, sure, but not that famous. And in one of these coffee breaks of faculty and stuff, he told me that at that time, they were a little bit disappointed with the result because it didn't have impact. And then he learned that Berry was, these works by Berry, that he was exploring basically a thing which was entirely different. It was this adiabatic evolution of a quantum system. And he was concerned about driving a system slowly around some closed path, and what would be the consequences once you close a path. And then Berry found that that's a sort of sophisticated algebra, but he found that there is a phase, a non-trivial phase that is accumulated, and it has physical consequences. And this, for Berry, this was a slow variable, right? And the thing is, well, what if you think that this variable psi lives in a much general space? It doesn't have to be necessarily a time evolution. Could be just something else. And then this was the key idea for these guys to take the paper that they wrote, and basically I think was Komoto who contributed most with Thales and that. And they showed actually, and that was a very nice result. They showed actually that what comes inside the integration of the Kubo formula in the simplified model, actually you can associate with the Berry curvature. And then you can show actually that this guy here is an integer and is associated with a topological invariant, in this case, the Sherman. And they were very happy with that. So I think it's a wonderful story where things are developing in very different fields, and they don't talk to each other until somebody makes the connection, and not very connection, general connection, and it gets results from somewhere else to generalize something and advance your field. So at that time, people understood this topological ingredient and realized this is strong because actually the integer quantum Hall effect doesn't require clean systems. And so this has to be a robust feature against, for instance, disorder. Okay? And I guess this was a major contribution of these guys at the early times to identify that. So, and then the other piece is this, which was very famous, and how they came to Brazil. I think it was Encontro Nacional de Física da Maneira Compensada that Eduardo Miranda organized, if I'm not mistaken. And he talked about his stuff, and basically he put forward a model where you know, like you could have this quantum Hall effect without magnetic field. So it would just require some funny hoppings for instance, in a honeycomb lattice, you have some funny hoppings here and a funny Hamiltonian, and then with that you have this. You open a gap and you have this the same features as people have observed in the quantum Hall effect, and that the modern people know as Chern insulators. So basically, also here you can show in a simple way that you do an integral of the Brillouin zone over this invariant that is the relative of the cousin of the Berry curvature for the system, and then you get this guy. And he went further, and he actually generalized that and put a whole class of model Hamiltonians, for instance, that have a kind of the Dirac spectrum, and then just by tuning some parameters, he showed that actually you can go from trivial to zero gap and to topological. So you have a topological a phase transition, a quantum phase transition, just by changing this parameter R, right? And okay, so and this paper was dormant, was a sleeping beauty for many years, until these guys here actually understood that you know, like the other paper was for spinless electrons, and you know, electrons do have spin, and the Hamiltonian was hard to realize. But then they understood that including spin and doubling the manifold, and including spin orbit interactions, you could actually have a cousin of this model that Haldane proposed, and actually in real materials you have good candidates for the topological phase. Okay, so and then from there on the field really took off. Okay, nowadays we learned a lot of stuff. I mean, there's 15 years of literature on that, and there is this bulk edge duality. So you have a gap in the bulk, edge states that will carry your electrons and provide you with a finite conductivity or conductance. And furthermore, all this is nice because these edge states are topologically protected against different classes of impurities or defects, no? And this protection by symmetry is quite robust. And supposedly these guys, they should survive different kinds of, should be robust. We know that surface states exist in different systems if you compute just clean systems, but once you put disorder, they disappear. These ones, they survive. And there is a whole activity on that, in particular now with machine learning, and people are running these nice codes and analyzing integration of the Brillouin zone, et cetera, and they come up with you know, like lists of different materials that show these topological properties, and just by running DFT calculations, you have thousands of candidates for this. All this works. They rely on symmetry properties and rely on some integration of a given topological invariant over the Brillouin zone. Okay, and so it's a kind of a strange, because you know, like the field was born with integer quantum Hall effect, and the samples are quite dirty, right? And then all the theories developed for ideal systems, and so this always caused to me some kind of perplexity, and then so this is what attracted me to this kind of questions. So there is a realization in 2D. I'm not going to talk about 3D. There is a realization in 3D. This famous Koenig paper in Science. And they basically they analyzed mercury telluride a quantum well, and depending on the width of this quantum well, the system shows this nice quantum spin hollow topological insulator features, and they show this quantized conductance, right? This has been already 15 years, more than 50, almost 15 years ago, and this conductance is never as quantized, perfectly quantized as in the quantum Hall. People have done a lot of work in getting it closer, but it's still kind of noisy. And these experiments are extremely difficult. And it's kind of annoying because all this stuff should be topological protected. So it should be, in principle, from theoretical perspective, sort of not easy, but it should reproduce what theory gives you, right? And although this is old stuff, even the most recent ones, they are not. There is some noise here, always a little bit above. People speculate about decoherence and stuff like that. Well, we're working on that, but it's a different talk. Okay. So don't want to spoil other story. Okay, so this is the idea. So this is the experiment I want to show. This is the kind of picture I want to highlight the motivation of our work. So disorder leads to an absence of translation invariance. General TIs make sense. How robust is this protection? So once everything requires an integration of the Brillouin zone, what sense does it make to integrate of a Brillouin zone if you have a strongly disordered system? There is no Brillouin zone. And there are lots of people that prove, at least theoretically, that you add disordered, things work as expected. If you have a very strong disordered system, then eventually things go wrong, but you can understand, you close the topological gap, or the different things that happen, and things seem to be quite robust, right? So what the initial hope that you have ordinary metals, you add disorder, you have trivial insulators, and you have a whole beautiful things of theory of Anderson localization. In topological insulators, you add disorder. There is no new topological phase, apparently. Apparently, they don't necessarily go to trivial insulators, but all this is sometimes a little bit open, right? So, okay. So, and here comes, so this is the beginning of, after this long introduction and situation of the field, this is the beginning of amorphous topological insulator business. And this paper came out 4 years ago now, and actually caught the attention of several different people, including myself. And these authors here, their starting point is something very interesting. They say, okay, so if it is the Brillouin zone that bothers you, let me start with a random system, no Brillouin zone at all. And what they do is that the only ingredient they put is that they preserve is that in the short range, they have a Hamiltonian, the type binding Hamiltonian, that reminds you of the kind of Hamiltonians that were proposed by Haldane or by Kane and Malley back in the early days. Okay, so there is a lot of structure here concerning spin, and it would be like if you generate in a regular lattice a Dirac kind of fermion, but here you have a lattice which is actually a random lattice. And they call this paper amorphous, right? And well, this is not amorphous, as we'll see later. This is a random system. It's a non-crystalline lattice. I'll come to that a little bit later, right? And then what they do, is that they compute, for instance, the density of states. Well, this is the cumulative density of states. That's some boring shape. If they put periodic boundary conditions, what happens is that you open a gap. If you have if you have put the borders here, then the gap closes with this few states here. And for instance, if you plot one of these states, it's hard to see. Well, this is one of these states here in the gap. And the state has all this, the state is kind of localized, not perfectly localized, but the localization varies. But this large balls here, the large circles, they stand for a large density, local density of states. Okay? And that's what happens. So all these states in the gap, they are kind of edge states, if you wish. And then they run a calculation of the conductance, and they have a perfect conductance corresponding to this gap states or to the states within the topological gap. And these are the hallmarks of 2D topological insulators, right? You have edge states, you have a gap in the bulk, and if you compute the conductance of such a system, so you attach here and there two leads, for instance, then you have a perfect conductance. And this they have done for a number of different models. I'm just showing the model which is a cousin of the Haldane one, spinless electrons, but they have also different ones. I guess there is a question.
Yes. Just a question. What is the horizontal axis on the top right corner graph?
This one?
Yeah. What is n?
N. N is the cumulative density of states. So you integrate the density of states from the bottom of the band until the energy E.
Okay.
So what happens? Sorry, I should have explained that. My mistake. So what happens is that there is the bottom of the band. Well, it's not the real. So these are discrete states, right? So, but it's large, so it's dense. But for instance, this is the edge of the lowest energy state, and you start integrating. It has this shape, which is, I mean, the shape is not so important. Until we reach this point here, you see the mouse. And if you have periodic boundary conditions, and you have an infinite system, no boundaries, no edges, right? What happens is that then the next state appears at, there is a jump here, the next state appears at energy plus some gap. And then the states behave normally again. So there is a gap, right? And if you have open boundary conditions, this gap is filled, but look, the number of states here is small, right? So as you move on the energy, the number of states doesn't increase much, so the density of states is small, which is the derivative of this, of n with respect to the energy. And yeah, and these guys, they are characterized as edge states, okay? So we have reproduced these numerics. First I was saying, no way, it shouldn't be correct. But it's an easy model to, to price.
Yeah, just a quick question. Are these edge states chiral?
Chiral.
Yeah, like in the quantum Hall or the Haldane.
Yes, you can say that. You see, you can say that because what we have done not with spin, right, is that we see something which are something like helical states. You see that since the lattice is random, the arrows, they are kind of funny, but it's a little bit hard to see. But you see this if you project out the spin, you see a circulating current in this edge if you attach the leads here and there. Okay. Yes, you're correct.
I'm sorry to interrupt.
Yeah.
I'm looking at the same plot, panel A of this figure.
This guy.
There seems to be a particle whole sim, something like that here.
A part? Sorry?
The panel A, top right panel. So there is some kind of particle whole symmetry.
Yeah. It seems, but if you look closer, no, right? So actually, the graph is a little bit deceiving. And when my student first computed this, I was looking for this particle hole symmetry because it's a small graph here, right? And it's approximate but not true, and there is no reason for that. If you look at the structure of the Hamiltonian disorder, so there is no reason for that.
Yeah. Okay. Thank you.
Good.
Caio, just one more question only. If you mentioned that the Hamiltonian that is loosely defined there, if you change the parameters in a way that you could say that you are not anymore in a non-trivial phase, does this quantized conductance disappear?
Yeah.
Do you see a phase, topological phase transition?
Good question. Good question. Yes. So these guys actually they have studied. I don't have the Hamiltonian written here, but there are some internal parameters that you can tickle with and play, and then you have you can actually show that there are domains where things are topological, domains where they are trivial, and you can actually study some transition if you like, right? If you like, you can study some transition. But you see, all these parameters, they are not structural parameters. They are parameters of the Hamiltonian itself, right?
Okay.
So it's a kind of a game, right? It's but you can do that, sure. And they haven't really studied in detail the phase transition, but they have this phase diagram, and it's worth to say that. Sometimes this conductance doesn't work so nicely. There are a few exceptions. We don't understand why. But most of the time, I mean, we actually found few cases where it doesn't work. So, we don't understand. But this is all this is nice and interesting to study.
As you said, taking at face value, this is absolutely unbelievable, right?
Yeah.
That this could happen, because with all the, how can you talk about Brillouin zone and everything and do the integration and all that? Yeah.
Okay, guys, I think all this is fascinating, but it's not my work, so I'd like to move along, okay? It's a pleasure to talk about this subject.
Sure.
Let's go on. So, let me just say that in the meantime, I'm following closely the literature, and there are probably 20 papers on different models for amorphous topological insulators published in different journals, 20 or 30. And I selected just one, and this one here that appears in PNAS, Proceedings of the National Academy of Science, in December last year. And these guys started to worry about the following thing, saying, hey, look, I mean, if we talk about amorphous matter, we should actually not talk about, a random lattice. So amorphous systems, they do have short range order, right? And these guys went to big pain on at least getting the coordination of their lattice fixed. So they have a fixed coordination. But it's a long way. I mean, if you look at the structural correlation function here, it's very far from amorphous. But at least they get the coordination. So people are starting to say, okay, we learned a lot about these models, but we want to be a little bit more realistic and to put some more ingredients of a real solid. Okay, even though there is no Brillouin zone. I'd like to say one word about things that bother me for a while, and then this is concerning the topological invariants. So the recipe that you want, that you have, is that you integrate of the Brillouin zone some function that is given to you, right? And then if you get an integer or so, you are characterizing a guy that is topological or not, okay? If you don't have a Brillouin zone, what people have done is that they use a kind of a supercell method, so expand this Brillouin zone and basically do this. So you take a big guy, and then eventually, if the L is infinitely large, which is never the case, then you don't have to integrate over the Brillouin zone. You just take one representative point, the gamma point, will tell you everything. Okay, so you have to do something in between, but this is the standard procedure that people do, and this is actually what we do. There is another one which is smarter and a little bit supposedly more profound, is this bot index, which is the real space representation of this integration. So people went to the pains of showing that, for instance, if you take the Chern number, then you can have an integer, a representation in real space that looks like that, where these are these matrices here. And the bot index can be generalized even to a spin bot index, so you treat real materials, electrons with spin. The thing is that you really need big chunks of you need to do this integration of a large space, if you want, this over what would be equivalent of several Brillouin zones, if you wish, even if you take a clean system. But this is not a problem, because if it is well defined, this is more comfortable than that, because you don't play tricks. You just compute your system and you integrate over whatever you have, right? And this is the spin bot index, okay? Okay, so these are, I personally like this one, which is a proposal by old proposal by Saint-Joseph, and which is computing this topological invariance using Green's function. This is very expensive. You can show it within the single particle scenario that is equivalent to whatever Z2 or Chern number. You can find expressions in terms of Green's functions, but you can wish that eventually you can generalize this to interacting systems if you wish, or even to amorphous systems. But we have been struggling with that for a long time because the integrations are, really terrible. Okay, so concerning experiments, there are 3 experiments that show that there are some amorphous topological insulators. This is, some people like to call this an experiment. This is a metamaterial, which is a meta-experiment, if you wish. So people construct metamaterials with the properties of the model of Argavala. And then, not as a surprise, they see physics like Argavala, the PRL guys, they predict. This is a little bit more interesting here. People have measured properties of granular films, and they see things that are consistent with topological properties in 3D systems. These are not really 2D. There is another experiment that, to my opinion, is nicer, also with bismuth selenide. It appeared in the archive last year, but it hasn't been published yet. So apparently, I'm not an experimentalist, but I guess they have been criticized by some things they have done in the experimental side. But from naively reading, they have observed in an amorphous bismuth selenide system 3D topological phase, if whatever they report is correct. So I didn't put it here because it's not published, and in my previous talks I have it, but since it's taking so long to be published, I guess there is some problems there. I refrain to show it to you, I guess. Yeah, in case. Okay, so what is what's our approach to that, right? Before we do, just as my criticism on most of these theoretical models, I mean, they they call these guys amorphous, but they disregard the whole literature on amorphous materials that started in the 30s of last century, almost 100 years old, right? So in semiconductors, people have done a lot of work in the 70s, 80s, and 90s, including people, I guess, Tomé maybe have done, Tomé Schmidt, even Hiroki. I know that Beto Fazio was involved in that. And basically, the key elements there is that there is a very standard model, which is the random network model. I'm not sure about talking about that now. And people have done molecular dynamics with classical empirical forces to find, the structures. And back then, they would do for 1,000 atoms in 3D systems in the 70s, 80s. And the simulation, very poor simulation, looking at the radial distribution function. Now you take one guy and see where the next neighbor is. Will give you 50, 60 years ago a nature. So you do this simulation here, and basically what you see is that the system retains the memory of the nearest neighbors. It knows more or less where the nearest neighbor atoms are, and eventually, once you go far away, all this is washed, right? And this is not something that the oldest models that theorists have been considered doesn't include that, which is a pity. So, well, let's keep calling amorphous, but okay, this is more like the same. So there are books on that, and characterizing short range, long range structure. From the quantitative point of view, this is this radial distribution function. If you have a perfectly organized crystal, you see this peaks. Once you have a glass, you see this. And if you have a gas, a random network, you see that. And this is what Argavala does in 2D, and most of the people. So they don't have that. So it seems more ordered than actually this. Right? So in any case. And then this is what we have been doing the last 2 years, trying to find candidates, at least in 2D, for realizing this topological insulators in an amorphous phase. And what are the main characteristics for that? So there are many, many materials in 2D that are candidates for 2D, for quantum spin Hall, and have been actually observed, right? So the idea is now you need to have something that you can actually grow relatively simple, and you need to have a real big band gap, topological band gap, otherwise it won't survive. And this is the summary of our findings. So in the clean systems, this guy here, Bismuthene, a single layer of bismuth, grown over silicon carbide, it becomes really flat, and it has, it is a candidate for a topological insulator. Theorists have proposed it, and experimentalists have measured it. And this is a very famous science paper that people have shown all these characteristics of quantum spin Hall in Bismuthene. So this guy in a clean phase is a topological insulator. Now, what these guys do actually to create this material is they do a lot of annealing. That's interesting, right? So it starts with something else. They do a lot of annealing until it's really clean and organized, and they see all that. So to get it beautifully on the plane and stuff like that. So, and that caught our attention because we thought, okay, so if they don't do so much annealing, they don't have something disordered or even amorphous, perhaps this is the chance to say, hey, don't do such a wonderful job. Stop before you anneal it entirely and try to measure, right? And that was our motivation back then, 2 years ago. And then this is the work, right? So with Márcio Costa, who is now at UFI, Gabriel Schroeder, who is a student of Beto Fazio. This is Nardelli, Buongiorno Nardelli, who is Texas. He's doing a lot of, well, I'll explain what he does. myself, we started with the following model. We start with Bismuthene, and we use one of these models that people are happy with to generate amorphous materials. So we start flipping the bonds. Every time we flip the bonds, these guys are really good at DFT calculations. They do a full relaxation using DFT calculation. So it's a heavy computation using, that takes into account all the properties of the material. And then after a while, you analyze what you got, and you got a very disordered structure. So back then, the computational capability was of treating 10 by 10 atoms, lattice, which was 400 atoms, because you have also hydrogens here to passivate the bismuth. So small lattices, actually. But even though being small, if you look at the paired distribution function, you see this nice thing. You retain some information about the nearest neighbors, and then it disappears. Then there is, if you have a perfect system, this would be your diffractogram, right? You see these Bragg peaks. And once you have this amorphous system, this is something else that people like to see. You have this, you lose this directionality, and you see this concentric rings, right? And the Z2 is preserved, and I already told you that we do it in a supercell. And this is the distribution of the ring sizes, okay? So you still have lots of hexagons, but then you have pentagons and heptagons. Back then, we didn't know, you keep with these amorphization steps. You go along. It was very expensive. At some point, we thought, well, we have enough, the system is already amorphous, and we stopped the procedure. Actually, we stopped also because we didn't have computer power to proceed, right? And we were happy to see this distribution of rings, which was consistent with, for instance, amorphous carbon or other 2D, amorphous graphene and other kind of 2D materials that you can easily generate in an amorphous phase. But actually, we were facing this question, well, why did you stop? If you do it, is there something more amorphous? If you go ahead, you actually destroy the amorphous phase. And so that was the thing. Incidentally, just a very short parenthesis, and this is on the way. So concerning amorphization, recently we learned with these guys that there are a whole class of paracrystals that live in the world between really clean systems and amorphous. And what happens is that this guy, Hosemann, understood that although you keep the short-range order, there is some mid-range or some medium-range statistical measures where whole lots of materials, they are not yet amorphous, and this transition goes smoothly. So there is a way to simulate, and that's interesting, a way to simulate. There is this disordered model that you can simulate how a system goes structurally from crystal to amorphous, going into this class that people call paracrystals. And this is the route I'm exploring with these guys, trying to understand the structural changes, and if this goes into a quantum phase transition, etc., etc. So there's some activity on that, but we would like to retain the structural properties and not going all the way to a gas, a Boltzmann gas. Okay, but closing this parenthesis, it's just to show that. These guys work hard. There was Marcio Costa did run a lot of simulations with this realistic amorphous topological model, and then run this fully relativistic DFT parameterized into a tight binding, or so. This was the contribution of Nardelli. And then if you look at a flake of this material, playing the same kind of games as Argavala did in the past, you see this kind of thing, right? So if you have periodic boundary conditions, then you open a gap here, and we compute the states. When you have open boundary conditions, we compute the states here, and they show this Z2 topological phase. And if you compute the conductance, it's quantized within this green region. And this is a realistic calculation, semi-realistic, of Bismuthene. So that was the nanolattice. And the questions that we have to answer is, what happens for larger system sizes, because the systems were fairly small. And then the other thing is how to better characterize the finite size amorphous systems. And this was before we didn't know how to compute the spot index, and now we do. And that's the more tricky one. What happens to the structural properties as a function of amorphization? Can you understand what happens if this is a continuous or non-continuous process? And for that, we need a different model how to play things. Can you identify a phase transition? And lastly, how robust is the topological gap? And it took us a year, more than a year, to actually come up with some of the answers. And since my time is running up, and you kept asking me about a paper by a different set of authors, just flash the main results here. So we did now with 1,000 atoms. So that was a big difference. Before we had 400 counting the hydrogens. Now it's 4,000 bismuthene. So the system is almost 10 times larger. And then we run this standard statistics here by doing this amorphization process. We tested different measures, and we understood that the ring distribution is still a good one for characterizing this amorphous phase. And funny enough, you see that we have different realizations. If you see these holes, right? How do you define a hole, right? People in the FT have different criteria to say if there is a bond or not. For me, it was like, there's always some hopping matrix element here, but they were telling me that this is an actual hole in the structure, and they convinced me that, like looking at semiconductors with holes, this is a very important thing to make solar cells, actually, and these holes are real there. But I'll show you something more interesting, more convincing than that. And then the idea is, oops, I missed that. Oh yeah. So I want to show this, and then I try to erase. The next figure is the one that I want to show you full. But if you take the full spin-orbit interaction, what happens is that as a function of our amortization step, there are some fluctuations here in the band gap. It seems that we will close. And at that point, I got very disappointed. I said, oh, if you keep amorphizing the guy, then everything disappeared. But then it recovers. And for the different samples, we see the same kind of feature. Right? It never closes. And in order not to close the topological band gap, you really need to start with a big topological band gap of order of electron volts. If you have anything which is small, then it will close. And so this restricts your choice of good candidates for a 2D amorphous material with topological properties, okay? So this is related to disorder. Sometimes the disorder is so strong that things, the ring sizes explodes, and some realizations might even go wrong, right? But from what we saw, as you increase the system size for different system sizes, as long as the band gap is sufficiently large, it doesn't close. And then we did something that, is there any DFT guy in the audience? Sure. Well, then we did something that in DFT is strongly forbidden, right? We played with the strength of the spin-orbit interaction. So this is a kind of a sin for DFT. So DFT is a first principle, so you're not allowed to play your system parameters. But we actually played a little bit. And what we learned is that if you make the spin-orbit interaction weaker, then obviously the topological band gap will shrink, will become smaller. And what happens if it's sufficiently small in this situation like here, as a number of amorphization steps, at some point it's no longer topological. So in between here, this is a stroboscopic picture, so it's not a continuous transition. But between here and here, something happened, the gap closed, and you have a quantum phase transition. And from here to here, we don't have this data, unfortunately. But at some point, the gap closed, and it was topological, and then it's normal. Z2 is equal to 0 and keeps 0. So all this magic is gone. So in this sense, you need a large band gap. So and actually for Bismuthene, in all the realizations we run, all the things, we never saw gap closing. So this is good news. And this is the same as before, right? So this is a graph like, I think, it was Edson who asked me. This axis here is the state index, the number of state, and this is the gap. And then if you take one of these guys here, you see this nice state, and it's concentrated as the edges. If you take one here, you see it's concentrated at the edges. And this guy here is more interesting. No, see, everything is boring. No, this is more interesting. Why? Because you see that it's concentrated at the edges, and it's also concentrated at internal edges. So actually, there is a hole there. Right? So if you crank up your machine in a 2D system, you build holes, and you have this. Eventually, you have these holes inside. So here it's not sufficiently far apart to really characterize a hole, but here it is. Right? So. And this is actually very bad news for topological protection, because eventually you can hop from here to there and destroy the quantization. Because if you have hopping matrix elements, you can do it. And actually, I think this is the doom when you consider, for instance, variable range hopping here. So if you consider Landauer, then you are fine, as you show in the next. But if you have finite temperature, and you have, and you think about variable range hopping, then probably the scenario is a little bit different. So to calculate the transport, so people worked hard. So they did a lot of Lego calculations. They were patching all these guys, and you have different realization. I think we had 10 different, and they become combined into very long wires by choosing at random these guys, and we can play all sorts of games. And eventually, if you take, this was a very long wire, almost 1 micrometer long, and you see that although you might have some destruction of the quantization here, overall in the middle of the region you have a perfect quantization. So this was a tour de force kind of calculation. So this is so we come to an end. No? So we understand that now, although there are many materials which are have been proposed as and observed actually properties of being 2D topological insulators, quantum spin Hall, at least the spectrum of them. If you look at the dispersion relation experimentally. In order to survive the amorphization, we really need a large topological gap of order of fraction of electron volt. If you go, for instance, to these quantum wells, the original ones, these are too small. Few milli electron volts will do the job. And that's it. strongly disordered systems show these topological properties despite not having anything like a brilliant zone. Right? And still, I want to emphasize that if you want to understand the phase transition, how things happen from the point of structure, then you really want to look at more relevant topological invariants. For instance, there are a whole discussion of local topological invariants, more local than the Bott index. And if you can actually extend that to these systems, I think we'll be doing a good job. So I guess that's all. This is my acknowledgement that these were the people involved in this effort. The two works that I reported to you were conducted mainly by Bruno and by Marcio and Gabriel. One of the works, there was a contribution by Marco, and Victor Regis is a new student I have at UFRJ while I crossed the Guanabara Bay, as George says. Okay? Thank you very much, people. Yeah.
Thank you. Thank you. Very nice talk. You had already some questions, but I am sure there are many more. So we are open to questions.
Can I make some questions? Sorry.
Sure.
Sure.
No, Tobias has seen this talk more than once, so he's improving his questions, and it's getting more and more difficult for me to answer. Go ahead, Tobias.
So thanks for the very nice talk. So now I like the first thing. I mean, the last thing that that's very like preoccupying, right? I mean that if you say that in the end you can have like if you have too many holes, you get some, let's say, activated hopping through the system, and that destroys everything. Now, in your calculation, you will never see this, right? So
this calculation.
In this calculation, exactly.
This calculation, yeah.
So what is your feeling? I mean, you just continue, and then I mean, this is serious, right?
No, this is everything is serious, Tobias.
No.
Come on. No, the thing is this. So this is my. I mean, you asked me. This is my very personal view. So right. The experiments have been at least in 2D. In 2D, there are few experiments, right? Concerning transport, right? Few experiments in transport, and they have the quality of the results is you know, it's a little bit disappointing after so many years, not to say very disappointing. And there are many different theories that conjecture why things are not working so well in these systems, right? So concerning Landauer approach, right? If you use the Landauer approach, then basically it's hard to explain why things don't work as expected, right? And there are a whole bunch of papers you probably know by Glasman and co-workers, even Felix von Oppen, that were thinking that even in this old experiments in the quantum wells, there might be charge puddles and the formation of some quantum dots. And then eventually many body effects will set in, but always there's many body effects set in the scenario of a variable range hopping. I mean, you need some activation energy, and this is the way Glasman likes it. I don't know. So you might have these localized states, and if you access them, and sorry. Let me open a small parenthesis. So when we do the calculations, right, we see that there are localized states within the topological gap. But these localized states, they are kind of in the bulk somewhere, and therefore the Landauer-Bütke picture doesn't catch them, because if you consider just elastic scattering, the edge states don't connect to these few localized states, and there is no backscattering due to that. But if you think about thermal activation, if you do a better job, then I think, yes, this could be an explanation. And we're actually working on that. We're combining something that hasn't been done before, in the sense that all these papers by these guys that do variable range hopping, they are very, they don't have any microscopic elements in there, system specific, or, where are these guys localized? Is this order localized in these guys in a sufficient way so that you spoil your conductance? And so we are mixing elements from microscopic calculation model population with these ideas to start to come up with some explanations why, after so many years, experiments are performing so poorly. So, okay, so these are my thoughts on that, Tobias. So is this, does it answer your question?
I think that Tobias is gone.
Oh, Tobias was so upset with my answer that he left.
He left. I think he had to go help his son. I think he here has a question.
Yeah. Hi. So,
yeah.
Very nice talk, Carlos. Caio, I didn't go away.
Stay. So, if you ask it, then you go.
By the way, there is a question by John Victor.
Okay. Can I go, or should he? Is he first, or should I go first, or what?
Yeah, João Victor Ferreira. Can you ask the question yourself? He says, he asked if in slide 33 are the black and white insets LDOS.
Sorry, I'm having problems with the mic, with the phone. So yeah. What is the question again?
In slide 33, are the black and white insets LDOS?
This guy. This is 33, right?
Yeah.
So the black and white.
I think it's the X-ray spectra.
Yeah, this should stand for the X-ray spectrum, right? So these are the bright points are the Bragg peaks. So if suppose that it's hard to do an X-ray experiment in these guys, but in any case, if you do that, then you should observe this in the diffractogram if you have a clean system, and if you have an amorphous system, you blur these peaks in this way. So you basically see these concentric rings. It's not a density of states. It's a different kind of thing. Right?
Tobias is back. You can scold him if you want.
My internet. Sorry, guys. But I got the response. Sorry, Kai. But
what was the response? We were speculating actually that you didn't like the answer, and then you decided to leave. So you felt offended.
But can I make another question, or I don't know actually if I'm okay.
Yeah. Go ahead. Oh,
just on the topology invariance. There's another simple idea, right? But maybe it's also not practical. But if you take periodic boundary conditions and insert fluxes, and then calculate it this way, do you know this?
No, the idea that sorry.
Which should also work for whatever. If you have disorder, and people used to do this for disordered system, right?
Yeah, the thing is that if you have a disordered system, then the simplest idea you can take is to expand your Brillouin zone and do periodic. Yeah.
Right. But
because if it is too small, then so it's this kind of thing. And then you integrate. You take one single representative point like a gamma point.
But if you don't want to like make the supercell, then you could also just take your original system and make it periodic with inserted fluxes, right?
Yeah, yeah.
I don't know if this is doable or more complicated. I just wanted to know if you know about, like, in practical, if this is practical or not.
Well, I'll tell you, no, I don't know exactly what you're talking about, but the thing is that we have a system which is not that large, right? And we work with that. We pretend this is a supercell, if you want, the system we got, and then we do the calculation for that.
But like in the like normally in disordered systems, people like to do this, right? I mean, like the 2D system, you look at periodic boundary conditions, cylinder, and you insert 2 fluxes, which then you can use in the same way.
Yeah. Okay. No, I understand. Sorry, you just yes. No, we haven't done that. We follow it. Well, we do this rough stuff.
Okay.
Yeah. So I'm not sure.
I was just wondering if this is practical or if this is like, I mean, then you have to add all these phases to the hopping element. I don't know if this is just something practical or.
The thing is, no, I don't know the answer. The thing is that we need the large systems to make a point anyhow, because in order to characterize this amorphous space with less than 1,000 atoms, 1,000 sites, it doesn't make sense. And if you have 1,000 atoms and 1,000 sites, or the corresponding orbitals, this is also good enough to calculate the spin bot index, the bot index, or even the Z2, the way I explained. So if you have a toy model and you want to do many realizations and stuff like that, and you want to optimize your work, probably you have to think harder in the lines that you are saying. But I haven't done it.
Right. Just the very last thing. I mean, do you know this work by Anton Akhmerov, who also looks at amorphous top? It's interesting, right? The idea is that you can restore. I mean, you have on average symmetries conserved, so you can restore certain surface states and all this. So that's a very interesting direction, right?
Yeah, that's a very interesting direction. So this is one of the creative things there.
Right.
Yeah. Well, that's a nice work.
Thanks a lot.
Luis?
So now just to go back to the amorphization process. So the original system with no disorder, Bismuthene, right? Is it a Caio-like topological insulator already? Do you have edge states? Okay. Then you have all defined Chern number from the brilliance up, right? So I understand from DFT it's really hard to calculate these Chern numbers.
Z2,
by integrating over the brilliant zone, because you might end up with only a few points in the brilliant zone, and you have to do like a numerical integration of very few points. So usually people do the Pfaffian route, right? Write the Hamiltonian, calculate the Pfaffian. Can't you do that in the disordered case as well?
Yeah. So basically, that's, I mean, I haven't done that, but they use exactly this Z2 code that was written by Vandervelde that does that for the super lattice, right? So that's in practice, this is what is done. And actually, it has some connection with what Tobias was asking. So in real materials, people, I mean, DFT people have developed codes to compute this topological invariant, which are incredibly efficient, right? Exactly because of the reasons that Luis was saying. If you do a calculation, like, you know, like computing the integral of the whole brilliant zone with even with lots of representative points, it's not very accurate and it's very expensive. So people have found ways around, and this is applicable also if you have a supercell, because it's a brilliant zone again, right?
But then you could start from the clean system, calculate it, add a little bit of disorder, and you know the numbers should not very much. That's my point. That you can go from the clean system to the disordered system and keep calculating this discharge number during the process of amorphization and see if
yeah,
right?
the thing that I didn't say, and it's interesting, this amorphization, is that actually all the strategies that we use in theory to generate an amorphous system, they are kind of non-adiabatic. I mean, you require a jump, you move two atoms, and then, I mean, the procedure is, I'm just describing the procedure, one of the standard procedures. You just destroy a bond, you put the atoms, you perturb them enormously, you destroy locally the structure, and then you let it relax. And eventually, you see that the structure that you obtain after relaxation, the metastable structure that you obtain, is very different from the one that you started from. And then you do this in different points in your system. And so every time you do that, it's not an adiabatic process. That's the point. Locally, it's very dramatic. And so I kept arguing with people about, with disorder, there's always this argument that, okay, so with disorder you have a topological structure, you do disorder, you basically can think that you switch disorder very slowly and then you modify. And as long as you don't close the gap, right, by doing that, you preserve the topological properties. Yeah, indeed, this is a way that people picture why these guys are stable. Just don't close the gap. But here, I have a hard time, picturing this because it's not an adiabatic change. It's hard to, to implement that in that way. And that's also the beauty of the thing. So actually, I think in the early days, people already discussed Argavala, and these guys also thought in these lines.
Yeah, and the transport part is going to be interesting because somebody's Edson, you have your mic open. Edson? Oh, okay.
No, not mine. Not mine.
Not yours. Okay.
No, it was not mine either.
Okay. No, just the question of transport. That peak of 2e squared over h, that's, some people think it's not really there. I mean, it's confirmation bias or something. Like, because many other experiments, people in Zurich, people here at USP, they tried, and it's not, as you said, it's not stable. So it would be interesting to see what your transport calculations show of the distributions of these conductance plateaus for these edge states there.
Okay. Yeah.
Gerson has a question.
Yes. Can you hear me?
Yeah.
Yeah.
Oh, okay. So first, thanks for the very nice talk. I managed to see half of it, the second half. So I lost the introduction, but I got the picture. And I think my question is related to the one from Luis regarding the transition from some adiabatic transition from topological to non-topological. There is this picture that says that you can actually show, define the topological insulator, comparing it to the atomic limits where nothing is coupled, like atomic sites that don't couple to other sites. So maybe in the tight binding model, you could manipulate the hopping parameter, reduce the hopping parameter, and then once the hopping parameter is very small, there will be no chemical bonds between the atoms, between the sites, and you might reach back the atomic limit. So as you increase, let's start for a very small hopping parameter, and then you increase the hopping parameter, and then maybe you can see the gap closing and opening to realize the topological phase transition. That may be a way to see it instead of using this periodic and open boundary condition procedure, just by manipulating the hopping. What do you think?
Yeah, you have two, basically in this very simple models, you have two energy scales. One is set by the hopping, the standard hopping that you have, and the other is set by the strength of the spin-orbit interaction. And actually, most of the stuff, I mean, BHT in the Kahneman and this kind of scenarios boils down to the competition of these two scales. Both have the right, I mean, you have the right stuff, but the interplay between these two parameters are fine. Now, the problem is that if you consider local disorder, like background, chemical background, things absorbed, etc., then it's one thing. If you consider that the atoms themselves will move around, and there are fluctuations in the hopping terms of even the absence of spin orbit, and then these fluctuations themselves start to dominate the effect. So actually, there are too many scales in this for me to play to give you a good answer. So if you make these hoppings very small, the fluctuations also are small, and then I'm not sure if you are able to understand the physics due to disorder. So because these two guys come together in the cases we examined. So I'm not sure.
Okay, thank you.
I have a quick one. What is the? Did you try to do this bot index calculation, or you never tried it?
Did I what? Did the program?
Did you try to do this bot index?
Yeah. So this is one I didn't in the first paper no, but in the second yes.
Okay.
And actually we do it. So here, so these guys they are about to add this routine to compute the bot index to this package in the FT, and they'll publish it or something. But the thing is, the bot index performs very poorly if you have a clean system. That's an interesting part. So because you integrate over, it's a local integration in the real space. So if you integrate over a primitive unit cell, it's small and it doesn't converge nicely. So this is a kind of showing how it works. Suppose this has something to do with, oh, this is the parameter. No, this is not the graph I wanted to show. So this is not the graph that explains what I'm saying. But the idea is that you see this, I mean, if the Z2 jumps, right, as a function of some parameter of the Hamiltonian, for instance, in this case. And it jumps very sharply. And this red curve is this bot index. Forget about the green, which is it's not interesting. If you do it right, the red one is the bot index, and you see it's kind of smooth, and it becomes sharper and sharper as you make the domain of integration larger. And so for people doing clean systems, the bot index is no good. But if you're interested in disorder, then actually you have large systems, and this is a good way to see it, competitive to supercell.
Okay.
Oh, Sergio.
Yeah, I see that Sergio is there. Yeah.
Hi, Caio. Thank you. I have a question for you.
First, where are you? In which part of the world?
We're in Copenhagen.
I came here.
Where?
In Copenhagen. Copenhagen.
Yeah, I wouldn't have guessed. Sergio, I mean, I'm talking about topological systems and edge states, localized edge states. Sergio is one of the Sergio and Nancy are the most delocalized people I know.
That's right. Here she is.
Hello. Sorry.
Yes. Hey, no, that's right. It's been interesting this year. No, I had a question for you on the, people, for example, if you look at tungsten ditelluride or these topological insulators in 2D that will give you edge states, then and will give you a spin hole, quantization. As you were saying, the experiments, even in supposedly good films, are, let's say, not very well quantized, right? So there is suggestive quantization, but on the other hand, your results will suggest that disorder somehow doesn't kill the effect. In fact, you need to really hammer it hard to kill it, right? That's what you're saying. So that seems to be a bit of a contradiction. I mean, so how come that if you have a crystal with a bit of defect, you have no quantization, not the topological invariance apparently is not as good, but yet if you have a disordered system, that survives. So how do you understand this?
Yeah, that's the question, Serge. That's the question. So the best papers, or the most plausible papers I've seen that address this issue is the ones that go beyond the single particle picture or beyond Landauer. Within Landauer and within, if you compute this with Landauer, no matter, we may ring, whatever, like the same, you get this incredibly robust stuff. But once there are some people that have been considering decoherence. There is the thing that I mentioned when I answered Tobias, many body and variable range hopping. And I guess, if you want me to bet, I think variable range hopping is the thing. So you have, you start having localized states within the topological gap. But in the scenario of perfectly elastic thing, etc., they are hard to access. And then eventually, if you allow for some other kind of mechanisms to jump, to hop, then yes. Because you see, you're at some given energy, right, low temperature, but this localized state is here. And so it's inaccessible to you, right? But if you allow some inelasticity or many body, blah blah blah, then you spoil the whole fun. But again, I'm speculating. It's we are among friends,
right. So you're kind of saying that in the nice systems, in the nearly crystalline systems, the temperature effect kills the conductance, while is that what you're kind of saying? Because see, the defects in those are personally weak, right? They make good crystals, and yet they're lousy quantized. But anyhow, so there
are some people speculating about decoherence as well, right? So if you think about even there is it's a funny thing. The other day I learned, if you look at this one of the papers by the Lewenkopf, the one that they look at the edge states, it's a Science on Nature 2009 with Sanjay Zhang, and they have supplemental material where they discuss the effect of the decoherence using the Whittaker voltage probe, and they see that the conductance is spoiled by adding some voltage probe that relaxes momentum. Well, the problem with this Whittaker model is that it is nice and phenomenological, but it doesn't tell you how the macroscopic mechanism why in hell would it relax. But if you believe in such a model, then yes. So actually, it's a kind of just a small parenthesis if you allow. So it's getting late, but. If you use the Whittaker model to analyze the integer quantum Hall, then you see that the conductance stays perfect, right? So because the chirality, you have this mode, and then you re-injects and it follows. But in the quantum spin Hall, it doesn't work that way. And in the supplemental material of this science paper, we discussed that. So the thing is, then you ask yourself, okay, so if they understood it, why isn't that popular? Or wasn't that widespread? It's not widespread because it's still lacking in microscopic mechanism. So if one can cook up everything together, then yes.
Yeah, you got a question?
Yeah, can I ask?
Get in the camera. I don't know.
What I really like about the talk is that you did a DFT study. And in DFT, you can see what happens with the orbitals. You really get into the dirty secrets of the material. Now, can these states be related to dangling bonds or phasor reconstructions that occur when you cut the material? Can you see? Because I always wonder what's the difference between these topological surface states and the TAM states or the standard surface states that people fought with many, many years ago.
So you're talking about this edge states, the nature, or this this guys here, this defense?
The edge states, because when you have a surface, you have either a surface reconstruction, because you have all these orbitals dangling there. The electrons have to somehow relocalize, reorder somehow, right? Because chemically you have different networks, right? And with DFT, supposedly, since they put the real atoms with the real orbitals, with all these ingredients, in principle you should be able to see how they change as you start adding disorder or your amorphization procedure in the bulk. Because some of these states on the surface are states on the bulk that are projected on the surface, but others are truly surface states. So I was wondering if you could distinguish, or if you look, since you did the DFT, the differentiation between the two, if there is a mixture, because it seems that since they persist, no matter what you do to the bulk, these seem to be truly surface reconstruction states.
Yeah. So I think there are many interesting questions to ask there, and I didn't really think hard about that. But what I've seen, and I was very happy to see, I asked these guys to do a thorough investigation in these materials, not Bismuthene, and in these disordered guys, of having the local density of states projected. You project over in a given site or a given point over all orbitals, and actually, if you do a little bit of smoothing, because you have this granularity of them, then you recover all these nice features of BHZ. It's incredibly good. No? So even the spread of the wave function of the local density of states once you go from the edge to the bulk. I mean, all these very simple-minded models with solving the Dirac equation and boundaries, they're not 100%, but for a given gap size, the size of the cloud decays within 20%, as you would expect from solving the Dirac equation. I was very surprised by that. But that is the only thing I actually asked these guys to do, because at some point we were wondering about the size, the width of the system we want to study. So what is the minimal width? So you don't want to spend a lot of computer time. What is the minimal width to be safe, right? And then I said, look, let's do this. Let's do a nice, and actually the predictions that you find in the early days papers, it's I think 10, 20% good for the real DFT ones, for Bismuthene, right? I'm talking about Bismuthene.
Interesting. Right. Thank you very much for a nice talk.
Thank you.
Nice
Thank
to see
you,
you
everybody
guys.
in Brazil.
Nowadays,
Yes,
this is the way you see people, right?
Yes.
I know.
And even here, because
Well, here we're actually in the apartment. We're working from home, so
that's why
we have meetings all day on Zoom. Yeah.
Yeah,
Okay.
everything is closed here.
Yeah.
So
For a few more days at least. Anyway. Bye, guys.
March meeting.
Bye, bye.
Bye, guys.
Caio, I have a question, but before that, I want to ask you. We are recording this, and eventually we're gonna put that on a YouTube channel. Are you okay with that? I have to ask you.
It's okay.
My lawyers have instructed me to ask you that. It's okay.
Yeah, if I knew, I wouldn't be so candid with the answers in the last part because I'm widely speculating.
Okay.
The good part is very few people will see it. I won't be embarrassed.
We hope not. We hope not. We hope not. The other thing is, if you could send me the file so I can post it together on our webpage. And I have a question. Have you guys investigated how large this hole has to be for the state to form, or in other words, how large is the hole before it becomes an edge? If that is an edge state. Yeah.
Yeah, I wish. I was intrigued by this, and these results were obtained very close to when we started to finish, and it became clear to us that there would be some relevance to them, but we didn't invest enough time in that. So I don't know how. I don't have an answer for that. But you see that's one thing that's interesting, because in DFT people have this feel for whenever two guys are sufficiently far, there is no bond. And they have even some criteria for that. They gave me some reference. I didn't have time to go into that. For me, it seems very arbitrary. But then looking at the local density of states and seeing that around these edges, the internal edges, there were some localized states, I thought, well, look, there is something to it. But, depends on disorder realization, all that. But it's an interesting question. How far should be the atoms be in order to form an internal state? Yeah?
Or to form an internal bulk, right?
Yeah.
Bulk of another another Z number. Well, I don't see any more questions here. So we don't need to close. We still have 24 people at least logged. If there are more questions, we are not paying you for the minute. So,
I wish.
Yeah. Yeah.
Thank you very much, Caio.
Oh, I got a coffee from.
Oh,
I will pose my suggestion again, that we get the address of the person who is doing the talk, and 10 minutes before the end of the talk, we order by iFood. We order a coffee for you. Why not?
Okay.
I like this. It will be a surprise for everybody. It's nice.
You gave the idea.
That's a big idea.
I gave the idea.
You gave
It's
the idea.
a good idea.
Yeah, it's a good idea.
Okay, guys. So thank you very much for your attention. Thank you.
Thank you very much.
Listening.
I'm gonna bug you for the file and
Okay.
for us to post it here.
Okay, beautiful.
I don't have to go, but I will go because I have a meeting.
I am actually in another meeting right now.
Okay.
The room.
Yeah, me too.
So I'll say goodbye then. Okay.
Okay.
So, okay. Bye, guys.
Thank you.
See
Thank
you
you
all.
very much.
Thanks, Caio.
Thank you very much.
Bye.
Edson.
Hey, the logo. for the logout.
You're gonna know about the YouTube soon, right?
Yeah.
Okay. Then
Let's go for a meeting. Let's go for a meeting.
Okay.